This is the third section now of the section on the course, of the part of the course about the polynomial method, which will itself be divided into two videos, both reasonably short. And they're going to be devoted to the discussion of a problem called the cap set problem, which used to be one of my favorite problems, but it has now been solved. And the question is the following. Supposing I take a subset of technical, being defeated by the technicalities of getting my pen to there we go, to be thicker. Right, supposing we have a subset of f3 to the n. The following is a known theorem. So it says that for every delta greater than 0, if A is a subset of f3 to the n of density at least delta, so that just means that the size is at least delta times the largest that it could be, then A contains an arithmetic progression of length 3. Now, what's an arithmetic progression? Well, it's a triple x, y, z such that x plus z equals 2y. But since we're in f3 to the n, and also we insist that x, y, and z are not all equal, because otherwise you get a rather boring, degenerate arithmetic progression. Because we're in f3 to the n, 2 is the same as minus 1, so that's also the same as saying that x plus y plus z equals 0. Which in turn is the same as saying that we've got an affine subspace of dimension 1. So they're of the form x plus a, x plus 2a for some a, the 3 points. Okay, so to say it quickly, a dense subset of f3 to the n contains a progression of length 3, or equivalently a solution to x plus y plus z equals 0. Now, the proof for a long time that was known of this used Fourier analysis and gave a bound for the delta that will suffice for the theorem to work of roughly 1 over n. And that was a theorem of Roy-Mechoulam. Although actually the proof was essentially due to Roth, who proved the same kind of statement, except that Roth's theorem concerns subsets of 1 to n. So if you have a dense subset of the numbers from 1 to n, then you can find an arithmetic progression of length 3. And questions about the best bounds in Roth's theorem are also extremely interesting. And if you go to the additive combinatorics course next term, you'll hear about those from Thomas Bloom, who along with Olaf Sisask is one of the record holders for Roth's theorem in the integers. And it turns out that Roth's theorem, his proof adapts very easily to f3 to the n. In fact, it's actually slightly easier in f3 to the n than it is in the integers. But the best known lower bounds were all of the forms c to the n for some constant c that was less than 3. In other words, they were exponentially small compared with 3 to the n. Or if you think of 3 to the n as being capital N, then you could say there were power type bounds in capital N. Exponentially small as a function of little n, but power small as a function of big N. But the bounds in Roth's theorem are more like logarithmically small in this big N. So there was a huge gap between, and then if delta is 1 over n, that's also logarithmic in big N. So the n is log of the big N. So there was an enormous gap between the best known lower bounds and the best known upper bounds, and this was what became known as the cap set problem. So a set that doesn't contain an arithmetic progression of length 3 was, for reasons that I can never remember, is known as a cap set. There was one small piece of progress before, I mean, small but very interesting and difficult piece of progress due to Michael Bateman and Nets Katz, which improved this 1 over n to 1 over n to the 1 plus c for some positive c, which was very small, something like 1 over 10,000 or something. But they managed to get I'm not even sure they calculated it explicitly, but they got a very slight a power type improvement on the little n. But that's not a power type improvement if you think of in terms of capital N. But then there was a sort of stunning moment, I think it was 4 years ago, which came in 2 steps. So one is that Ernie Croot, Seva and Péter Pach managed to find a proof that gave an exponentially good upper bound for the density that you needed, but not in f3 to the n, but in z4 to the n, so exponential in little n this time, for progressions of length 3. But that proof used somehow the fact that z4 to the n at 4 has a factor 2 in some funny way, and so it looked as though that was a very interesting proof, but maybe just a curiosity. But it only looked like that for a couple of weeks, because 2 weeks later, Jordan Ellenberg and Dion Gijswijt found an exponentially good upper bound in f3 to the n. So they in other words, I think it's still the case that the best known upper bound doesn't match the best known lower bound. In other words, they managed to get an upper bound of the form c to the n for some c less than 3, but not the same as the best known lower bound c, although there are related problems for which the exact exponent is now known. So what I want to talk about is the, oh, by the way, I should say that the Ellenberg-Gijswijt proof used in a very strong way the ideas of Croot, Lev, and Pach. So I think nowadays people sort of regard the result as being sort of due to Croot, Lev, Pach, Ellenberg, and Gijswijt, though the actual step that solved the problem was due to Ellenberg and Gijswijt. But the technique, the sort of really clever idea that changed the problem into one that could be contemplated as solvable, was came in the paper already of Croot, Lev, and Pach. Now there's one other name to mention here, which is Terence Tao, because what I'm going to present is not quite the proof of Ellenberg and Gijswijt, but an alternative argument that Terence Tao came up with also fairly soon after that, which was, so if we formulate the problem in terms of looking for solutions to x plus y plus z equals 0, we have a statement that's symmetric in x, y, and z, and Tao thought it would be nice if the proof were symmetric in x, y, and z, which the argument of Ellenberg and Gijswijt wasn't. And he thought about it and came up with a way of running the same sort of argument, but in a symmetrical way. And it's a rather beautiful argument, and it turns out that for some other purposes, for generalizing in some directions, it's more convenient to use Tao's formulation of the proof, or Tao's proof, which, I don't know, it's up to you to decide to what extent it's a reformulation and to what extent it sort of involves new ideas. It's certainly very much the same sort of framework as the previous arguments. So I'm going to talk in this video just about a concept that Tao used. You may even have introduced it, I'm not quite sure, I can't remember now, and then prove a lemma about that concept. And in the next video, I'll show how once you've got that lemma, it's a short step to getting an exponential upper bound for the cap set problem. So the concept I'm going to talk about is something called slice rank. But before I say what that is, I just want to begin by just thinking about what the rank of a matrix is. So of course one can just say it's the dimension of the image, but I want to think about it in a slightly different way, but it's equivalent. So supposing I've got a matrix and it'll be over F3, but of course this applies. Actually, maybe I'll just say it over a general field for the moment. So supposing I've got but I will make it a square matrix because I don't really care about the extra generality. So let's make X, but what I say will apply just as well to rectangular matrices. So if A is an n by n matrix, then we can define the rank of A as the minimum R such that A can be written as a sum of R rank 1 matrices. And what's a rank 1 matrix? So I'm going to think of, so one thing I quite like to do is think of n by n matrices as just functions of two variables where each variable ranges over a set of size n. So let's just write A x y, where you might normally have written A x y. So what we're saying is that it's the smallest r such that we can write A x y in the following form. Sum I equals 1 to r of ui x vi y. So a rank 1 matrix is one that can be written as just a product of two functions of one variable each. And then a rank R matrix is one, or a rank at most R matrix is one that can be written as a sum of at most R of these. And this we can write as, if you want to write quite a nice notation for this, is just to write it as sum I equals 1 to R ui tensor vi. So ui tensor vi is just notation for the function that takes xy to uix times viy. Okay, now I want to talk about a concept called tensor rank. So for me, I'm only going to go up to tensors of degree or order, I don't know what you call them, of tensors, 3 tensors. So these will be functions of 3 variables. So supposing I've got a function f x, y, z. That's sort of 3-dimensional matrix, something like that. I'd like to come up with a notion of rank for such functions. And it turns out that there are several competing definitions, not all of which I'm going to talk about. I'm just going to mention a couple. So the most obvious definition of rank for a 3-variable function would be just to say exactly what I said up here. It's the smallest r such that you can write f x, y, z as sum I equals 1 to r of uix, viy, wi, z, as a sort of product of, sorry, as a sum of products of one variable functions. And if you can use at most r of such products, we could say the rank is at most r. And this is a definition that is of some use. People work with this definition for 3 tensors. But it turns out that, well, there isn't actually a single definition of tensor rank once you get past matrices that sort of wins out over all the others. For some applications, one definition turns out to be good, and for other applications, another definition turns out to be good. So just to give you an idea, here's another sort of definition that's also not bad. We could say it's the minimum R such that we can write f as a sum. You'll see that this also is going to be a direct generalization of what we've got here. And you may be able to guess what I'm about to write. Sum I equals 1 to R of ui xy vi yz wi xz. So here I went to one-dimensional, so to speak, or one variable functions. Here I went to sort of n minus one variable functions, where n equals 3 in this case. So you can see that this is, it just so happens that 2 minus 1 equals 1, and so those two definitions coincide when we're just talking about two variable functions. And this is also a useful concept. In both cases, what we've got, we just sort of say slightly more generally what we're doing. We're defining a class of simpler functions. So we start with a function of 3 variables, and we'll say that a function is simpler if it's a product of functions of fewer variables. But what exactly we mean by fewer is different in these two definitions. So here we just mean any product of functions that have fewer than 3 variables counts as a basic function, and then we say that f has rank r according to this definition if we can write it as a sum of at most r basic functions. So just to say it again, I'm defining a basic function to be any product of functions of at most 2 of the 3 variables. Whereas here I define a basic function to be one which is a product of functions of just 1 variable. Now, slice rank actually isn't either of those definitions. Here, for slice rank, we say that a basic function is one that is a product of a function of 1 variable and a function of 2 variables. So it's a kind of intermediate thing. But because there are 3 possibilities for which variable we choose to be the one to pick out where we have a function of that 1 variable, it's a little bit less nice to write out, but I'll write it. So in fact, I'll write out a slightly more formal definition. So definition, f has slice rank at most r if we can write it in the form f x, y, z equals sum I equals 1 to r1 ui x vi yz plus sum I equals r1 plus 1 to r2 of ui y vi xz plus sum I equals r2 plus 1 up to r of uiz vi xy. So it's a slightly strange notation because the ui's are functions of x up to r1, and then between r1 and r2 they're functions of y, and between r2 and r they're functions of z. But I'd rather do that than have to choose 6 different letters. And it's actually not ambiguous when you think about it, because yeah. So that's what we mean by slice rank. And so we say it's slice rank r because the number of different basic functions we've used here is r. And I think I'm ready for the lemma, which looks extremely natural. And has a rather nice proof. So let A be a finite set and let f be a function from a cubed to a field f such that f x y z is non-zero if and only if x equals y equals z and that's all I want to say. then slice rank of F. So this is a sort of diagonal tensor with non-zero entries down the diagonal. The slice rank of F is the size of A. So this is a generalization to slice rank on 3 tensors of the familiar fact that if you've got a diagonal matrix, square matrix with non-zero entries down the diagonal, then it has full rank. When I say full rank, actually, why do I say that it's not quite so clear that we want to call this full rank here, because there could be functions of rank bigger than the size of A, but it's got rank that's the size of A anyway. So let's just quickly, first of all, do the easy direction. So in one direction, we can say, we can write f x y z equals the sum of all A in A of f a delta A x, delta A y, delta A z, where delta A x equals 1 if A equals x, naught otherwise. So you see that? So if x equals y equals z, then they will equal A for exactly 1A. And what will that contribute? It will contribute f x x x, because they're all the same, which is what we want it to contribute. And if x, y, and z are not all the same, then all these products will be 0, and we'll get 0. And of course, that we can think of this as a function of 1 variable times a function of 2 variables. It so happens that the function of 2 variables splits up as a product of functions of 1 variable, but that's okay. We have n terms in this sum, and therefore the rank is, n, we have size of A terms in this sum, and therefore the rank. What we've shown here, we've got an upper bound to the slice rank. We managed to find some way of writing f as a sum of the appropriate kind. Now let's show that we can't do any better than that. So now suppose that, let's try and make a lot of space. So f x, y, z is, write out this expression again. So I equals 1 to r1 ui x vi y z plus sum I equals r1 plus 1 to r2 ui y vi x z plus sum I equals r2 plus 1 to r ui z vi x y. And without loss of generality, r1 is greater or equal to 1. In other words, this is not just an empty sum here. Now, I claim we can find a function h orthogonal. I'll explain what orthogonal means in a moment, but it has a fairly natural definition. So orthogonal to u1 up to ur1, and this is a function from A to f3, or to f, sorry, it will be f3 in our application, but from A to F, orthogonal to U1 up to UR1, such that H A is not equal to 0 for at least A minus R1 elements A in A. So we can certainly find something that, so what do I mean by orthogonal? I mean with respect to the following thing, I say that FG is just the sum over all A and A of FAGA, where the sum is in the field F. So we can certainly find something that's orthogonal to U1 up to UR1 just by taking the 0 function, but I want something that's not trivial. In fact, I want it really to be quite strongly non-trivial. I want it to be, to have at most R1 zeros. So it's a piece of simple linear algebra. So what's the condition on H? If we form a matrix with rows U1 up to UR1, so U1, U2 up to UR1. So it's a matrix like that. That is an R1 by N, or by the size of A. Perhaps I should have just said at the beginning that A had size N. Matrix, and then I have H here, and we want that to be 0, but we also want H not to have too many zeros. And how do we do that? We note that this has rank at most R1. So we can put this into reduced row echelon form, and we will end up with a matrix that has if we permute the if we're allowing ourselves to permute the columns, which may mean that we have to permute the entries of H, we can then say that sort of without lots of generality, we'll get a matrix that looks like this. It has a sort of identity matrix here, S by S, and then it has its 0 down below and has some entries here, which we don't really care about. And now if I want to make this, if I want to solve this equation with not too many zeros for H, what I can do is I can choose all the values of H below the top S values. So I can choose all these as I like, and I'll get some, when I work out this matrix multiplication, I'll get some inner products of this bit of the vector with these bits of the rows here. And then if I want to make this 0, I'm then forced to choose the remaining coordinates up here in such a way as to get 0. So I have no choice about how I choose the top few coordinates. They might even all have to be 0, but I can choose these ones as I like. So I can just choose all these ones, let's say, to be 1, and then that will fix the remaining ones. And so since I managed to choose these as I like, I've got at least n minus s, keep saying n, we have that number of ones, and then s is at most r, so or r1. So the number of zeros is at most r1. So the number of non-zero entries is at least the size of a minus r1. Now, if I'd only allowed myself to do row operations, then I would have had this matrix here, but it would have just, these columns would, instead of being all bunched up at the beginning, would have been spread around the columns, and these top entries of H, the ones I got to choose, wouldn't be the first S ones, but be just some S things. So I'd get to choose all but S, and then the remaining S would be determined. Okay, so that proves the claim. And now what are we going to do? So now let's look at the function G from A squared to F, defined by Gijz equals sum over all A, H, A, let's call it sum over all X, Hx, F, X, Y, Z. Now let's have a quick think about what, so observe first that G has rank at least size of A minus R1 because GYz equals naught if Y doesn't equal Z. That's because fxyz will be naught for all X. And if Y equals Z, then GYz equals HY FYYY, which is non-zero, at least A minus R1 times. So we've got a diagonal matrix with at least that number of non-zero entries down the diagonal. Therefore, it's got at least this rank. But we're going to get an upper bound for the rank as well by considering the fact, which we haven't yet used, that, well, we've used it to define H, but we haven't used the fact that F is really written like this. Let's think what we have. So what are we doing? We're multiplying both sides by H and then summing over X. Now, what was the property that H had? It was orthogonal to all these UIXs. So when we sum over X, the sum here we'll get a sigma HX UIX, which will be 0. So this term is going to be killed completely when we take the inner product with H. This one, what happens here? We get the sum from I equals R1 plus 1 up to R2 of UIY times a function that we get from VI by taking the inner product with X of the sort of first variable, so to speak. So we'll get a thing that looks like this, sigma HX VI XZ. We don't know too much about that, but one thing we can say just from sort of grammar, so to speak, is that this is a function of Z. X is a dummy variable here. This is just a function of one variable of just a function Z. So it's some Wi of Z. And similarly, this one is going to be just a function of Y. So just to conclude, that term goes, this becomes a sum of the product of one variable functions, and this becomes a sum of product of one variable functions. So down here, but also GYz can be expressed in the form sum I equals R1 plus 1 to R2 of UIY WIZ plus sum I equals R2 plus 1 to R of UIZ WIY. And just to repeat, the first bit of this thing vanished because of H being orthogonal to the UIs that were functions of X. So G has rank at most the number of terms we've got here, which is R minus R1. So R minus R1 is greater than or equal to the size of A minus R1, which implies that, let's write it the other way around, size of A is less than or equal to R. What was R? R was the number of terms here in some way of expressing F. So that's telling us, actually, I should have written it around the other way around. More natural to write R is at least A, and R was the number of terms in some expression for F in terms of functions of 1 and 2 variables. So that's telling us that the slice rank F has slice rank at least the size of A. So it had slice rank at most the size of A, it had slice rank at least the size of A, so it has slice rank exactly the size of A. And I'm hoping that if you haven't seen this before, then you're thinking, what on earth could that possibly have to do with finding solutions to x plus y plus z equals 0 in dense subsets of f3 to the n? It is not, even at this stage, it's going to be a very short proof, but certainly not an obvious argument. But that will be a topic for the next video.